Yes.
They can come if they want. Oui. Bonjour. Philippe, tu parles en français?
Ouais, je pas beaucoup de. Je vais pas poser de questions.
Non.
Féliciter.
Généralement, ouais, c'est ça. Ok.
Il y avait des invités qui étaient perdus. Ils sont juste 3. D'accord.
No, yet I think.
Ouais. C'est bon, tout le monde est là?
Yes. Jeff.
Ouais.
Jeff here. Okay, there might be still one. Maybe.
Parce que faut quelqu'un lui ouvre. Comment?
Il va arriver en retard, ils vont.
Okay, en retard, ma بعرف.
ouais, je voyais bien. Oui.
Tu pourras, je vais te présenter le jeu vite fait.
Ouais.
Je peux faire un
Les
travail
afficher,
sur YouTube.
les afficher individuellement.
Ça, je crois que je peux pas.
Tu peux pas?
Alors, si, je dois pouvoir, mais. Un par un?
Ouais.
Ouais.
Pour qu'il les voit.
Tu saches qui est.
Alors, je pense qu'il faut les mettre en évidence.
Non, mais ils ne voient même pas les choses. Ils peuvent les voir au moins les quatre ensemble.
Il va les voir.
C'est-à-dire sur les
Sur YouTube, ils voient qui? Sur YouTube, ils voient la caméra.
Non, pas forcément. Il voit celui qui est
Parfait, so,
Mais si
Oui, mais
j'active,
ils ne voient pas.
ouais,
voit pas
si
les
j'active
youtubeurs.
un par un, ça va marcher, je pense. Mais
Voilà.
il faut que je sois réactif.
Start.
C'est dans quel ordre que tu
you
veux
can start.
You ready?
Yes.
Oui,
Okay. So, good morning.
Il est parti.
Là, c'est
Ouais,
bon.
c'est bon, on peut y aller.
Alors, monsieur Ali Hojeij, vous présentez aujourd'hui devant un jury de l'Université Grenoble-Alpes pour l'obtention du grade de docteur de la communauté Université Grenoble-Alpes. Okay, standing.
Oui, oui, j'ai compris.
You're going to defend your PhD. Okay. And, donc, je voudrais juste préalablement à vous laisser la parole, présenter les membres du jury. Okay, I'd like to introduce the members of the committee. First, your reviewers, professeur Wazili de l'Université de Lorraine. Second reviewer, professeur Arnaud Cox from INSA Toulouse. Then Miss Audrey Soric, assistant professor at Centrale Marseille.
Bonjour.
Mr. Stéphane Atou from Arcolia Energies Company. Okay. Cyril Bonamy and your supervisors. Okay. As you know, après la présentation, after the presentation, you will have also to discuss with all the members, to listen to general comments and also to reply to answers, right?
Yes.
So
I can start.
I leave you the floor and you can start for 45 minutes.
Okay.
Okay.
Okay, so good morning, everyone. Today I'll present the work I did during my PhD entitled Mixing of Thick Fluids by Gas Injection. The work was done in Laboratoire Rhéologie et Procédés and the Léger Laboratoire under the supervision of Monsieur Laurent Jossé and Monsieur Philippe Séché. So generally, the presentation is divided into 5 main parts. In the first part, I'll introduce the industrial problem and how we try to model it experimentally. In the second part, I'll present the result concerning the gaseous phase dynamics, mainly the bubble dynamics. In the third part, I'll introduce the results concerning the liquid phase dynamics. In the fourth part, I'll talk a little bit about the development of the numerical model. And in the first part, I'll finally present the general conclusions and some perspectives of the work. So let's start with the introduction. So in fact, what is anaerobic digestion? Anaerobic digestion is the decomposition of organic material by microorganisms in the absence of oxygen. The general field of anaerobic digestion is mainly agricultural waste of plant or animal origin. The products are mainly 2 products: biomethane or a biogas. The biomethane can be used for electricity heat production, vehicle fuel, or a renewable natural gas. And the other product is solid digestate, which is considered a nutrient-rich fertilizer and have many agricultural applications. So mixing operation in an anaerobic digestion process is a vital operation that aims at reducing the non-uniformities in the concentration, in the temperature, and increase the surface of contact between the substrate and the bacteria, further increasing the yield of the mixing, further increasing the yield of the production of gas. It can be attained using 2 methods. It can be attained either mechanically by the use of an electric motor and an impeller, and the impeller will steer the contents of the reactor, therefore inducing mixing, or by a pneumatic mixing, in which pressurized gas is injected inside the contents of the reactor. The rising bubble will tend to agitate the contents of the reactor. So in fact, pneumatic mixing holds some advantages or some more desirable effects over mechanical mixing. Mainly, it is a simpler design with fewer moving parts. This will cause it to be more cost effective in terms of operation and maintenance. It is also more process friendly, as the induced shear stresses are assured to be lower than the critical shear stresses tolerated by the bacterial culture. Our study in fact focuses on the Arco-Meta process. It is a novel anaerobic digestion process that implements pneumatic mixing as a way of agitation. We focus on the digester, the flow inside the digester. So the digester is comprised of a cuboid tank with multiple compartments and multiple injection pipes. Pressurized methane is injected inside the injection pipes, creating some bubbles that tend to shear the fluid around them as they propagate upward and induce recirculation in the tank. The substrate used in Arcolia Energy is mainly a thick sludge, fibrous sludge with high solid content of plant or animal origin. So in order to model this industrial problem experimentally, we used the experimental setup present at Laboratoire Rhéologie et Procédés. It's mainly made of a pressurized air reservoir, as well as a tank connected by piping system into a tank with transparent walls to aid in visualization. We also have a solenoid valve and a flow rate that allows us to work on a constant injection flow rate as well as temperature and pressure sensors. Finally, we have a camera setup that allows the capturing of the flow in 3 dimensions. So using the industrial material represent a health hazard and a logistical hazard. So in fact, we used instead carbobol solutions. These are aqueous solutions which are harmless and can be easily prepared and are transparent. So we start by preparing several samples. Then we did the rheological measurements of these samples. The figure here represents the flow curves for different samples prepared. This behavior can be in fact fitted into the Hojeij-Buckley constitutive equation. In the Hojeij-Buckley constitutive equation, we have a certain yield stress. Below this yield stress, the shear rate is 0, so the fluid remains unyielded. Above this yield stress, the stress and the shear rate are related in a non-linear manner due to the shear thinning effect of the fluid. So this table, in fact, represents some rheological parameters of the fluids that we prepare. Tau 0 is the yield stress, K is the consistency, and N is the flow index. So the video here presents the experimental observations, initial experimental observations. As soon as the injection starts, a gas cavity or a pocket of gas is formed at the injection point. This gas cavity will expand and collapse in a periodic manner, releasing the gas into a newly formed bubble. The dynamics of the gas cavity were studied in detail and published in American Institute of Chemical Engineering journal. But in general, the dynamics of the gas cavity have minimal effect on the overall mixing in the reactor. So after the gas cavity, a bubble is released, it propagates toward the free surface, carrying within its wake a small quantity of the fluid and shearing the fluid around it. When it reaches the free surface, it bursts, spreading this quantity over the whole cross-section of the reactor. So this gaseous flow will induce a liquid flow that can be summarized by the following. So we have mainly 3 main regions or zones of the flow in the reactor. In the blue region here, it is the rising fluid region, where the fluid tends to rise between 2 consecutive bubbles and around the rising bubbles. This upward flow rate is balanced by a downward flow rate, indicated here by the green region, inducing fluid recirculation. Sometimes a third region will develop if the reactor is large enough, in which the fluid will remain stagnant, mainly at the extremities of the reactor and at the corners. Okay, so just to elaborate more on the specificity of our flow, in fact, we have a unique reactor design in which we don't have a daft tube that will separate the rising fluid and the descending fluid regions. We also cannot control the bubble velocity, the bubble volumes. So in fact, we work on a constant injection velocity, and the bubble volumes are not controlled. We have a non-Newtonian fluid with a yield stress. Inertial effects, in fact, cannot be neglected. They play a role in the flow dynamics. The bubbles that are produced are relatively large, so the dimensions of the bubble and the dimensions of the reactor are comparable. And finally, we have a confinement effect due to the effects of the wall and the free surface. So the fluid domain cannot be assumed as an infinite medium. The final point that the flow that we have seems to be unsteady. So to sum up the forces that are acting on the flow, we start by the inertial forces, which is a result of a certain scale velocity u and can be written as rho u square in the units of Pascal. The viscous forces are divided, are the result of the fluid rheological parameters. So we have here the viscous force due to the consistency and the flow index, and can be written as a k gamma dot power m, where the gamma dot is the velocity scale over the length scale. The yield stress, it's already in the units of Pascal of the fluid, and the buoyancy of the fluid, and the buoyancy, which is a function of the gravity and the length scale, and can be written in units of Pascal as a form of rho gl. So the choice of the length scale and the velocity scale depends on the phase that we are studying. When we are considering the bubble phase, the length scale was chosen as the equivalent bubble radius, which gives a good estimation of the real bubble radius. The velocity scale was chosen radical GR. It comes from the assumption that for the bubble, inertial and buoyancy forces are equal, and it gives a good estimation of the bubble velocity. the aspect ratio of the bubble is always the height of the bubble over the diameter. For the liquid phase, the length scale is the width of the tank indicated in the figure here. The velocity scale, it's the gas injection velocity multiplied by a factor. This factor represents the ratio between the area of the injection pipe and the cross-sectional area of the tank. The aspect ratio of the reactor is the height of the liquid over the width of the width of the reactor. So we can write these forces in a non-dimensional way. We can start with the Reynolds number that represents the ratio between inertial and viscous forces, the Oldroyd number that represents the ratio between yield stress and viscous forces, the buoyancy represents the ratio between inertial and buoyancy forces. So this is the Froude number, sorry. And the yield parameter represents the ratio between the yield stress and the buoyancy forces. So I'll start now with the gas phase dynamics, which is the result concerning the bubbles. So for the bubbles created, we had two main observations. The first is that the phenomena by which the bubble detaches. So we differentiated between two detachment phenomena. The first is called a two-stage bubble detachment. In a two-stage bubble detachment, two consecutive cavities will collapse to create a single bubble. So in fact, the first cavity will create the bubble cap. The second cavity will create the bubble tail, creating this mushroom shape. Then these two cavities will collapse, creating an independent bubble that will rise toward the free surface. So this type of detachment was observed for fluids with low yield stress as well as for the Newtonian case. The second detachment phenomena, we call it a single stage detachment phenomena. It is simply that each independent cavity is responsible for creating a single bubble, and this is encountered with fluids with high yield stress. So generally, the two-stage detachment is encountered when when we have a flow with low yield stresses and high inertia, so a yield parameter lower than 1, and the single stage detachment is when we have a low inertia and high yield stress, so a yield parameter greater than 1. So this threshold at 1 it's not very strict. So at the neighborhood of 1, we can see some cases where we have the both phenomena happening simultaneously. So it's not that simple. The second observation is that as the bubble rises toward the free surface, its morphology and its aspect ratio will change as a function of time. So in the graph here, we are plotting the aspect ratio of the bubble as a function of time for the different fluids. We can see that for the Newtonian case and the low yield stress fluid 1, the behavior is similar. For the first 0.1 seconds, the aspect ratio will increase. The bubble at this time is inflating. The increasing buoyancy forces will tend to stretch the bubble vertically. At 0.1 seconds, the bubble will detach, so it will collapse into an oval shape, increasing the bubble aspect ratio, decreasing the bubble aspect ratio to around 0.75. After which, the bubble will continue propagating upwards, and its aspect ratio will continue to oscillate between these two values, keeping it an oval shaped in general. The change in the aspect ratio for a high yield stress fluid, as indicated here, it's much more evident. So in the first 0.1 second, the aspect ratio will quickly increase to 2.1. So during this time, the bubble is forming. The increasing buoyancy forces try to stretch the bubble vertically, and the high viscous resistance try to resist the expansion of the bubble radially. At 0.1 seconds up to 0.2 seconds, the bubble will detach and a portion of the tail will collapse, so the aspect ratio will decrease drastically. After 0.2 seconds, the bubble will continue propagating toward the free surface, slightly stretching vertically. So, in fact, in order to allow for a systematic reporting of the bubble dimensions and the bubble characteristics, we always measure or report the bubble characteristics when the bubble reaches HL over 2, or the mid height of the liquid, and the dimensions are always averaged over 30 bubbles. So let's start with the bubble frequency. The graph here, it plots the bubble frequency as a function of the injection flow rate for different fluid used. We can see first that as the injection flow rate increased from 2 to 10, the bubble frequency will decrease, tending toward a plateau around 3.3 hertz. 3.3 hertz. The effect of the yield stress, in fact, is more or less small or negligible, especially at high flow rates, so at 5 and 10 meter cube per hour. We can see a certain difference in the behavior between the Newtonian case, so the decrease is very slight and linear, and the non-Newtonian case, and this is probably because of the elasticity of the fluid. So in fact, in the yield stress, the bubble try to grab hold of the yield stress, keep for a little longer period of time, so it increases in volume. Therefore, we reach a constant viscosity, a constant frequency. Concerning the effect of the tank on the bubble frequency, we can see that as we increase the tank width, the bubble frequency will slightly increase to reach values of around 5 Hertz. So we try to represent the bubble frequency in a non-dimensional correlation as a function of the dimensionless numbers of the liquid phase. So STB here, it is the dimensionless representation of the bubble frequency. First, so we can see by comparison that both Reynolds, Oldroyd, and yield parameter have comparable effect in their absolute magnitude. So if we write them in their definitions, by their definitions, this equation can be simplified. We are only left with two terms: the inertial term that is in the Reynolds and the buoyancy term that is in the yield parameter. The effect of the viscosity and the yield stress will diminish. So finally, we can write this correlation in a more simplified manner as a function of only Freud number, which is the ratio between the inertia and the buoyancy of the liquid phase. So in fact, the bubble frequencies are governed by the balance between the inertial effects and the buoyancy of the liquid phase. So this correlation, in fact, allows us to finally get access to typical bubble frequencies. Therefore, we can calculate the typical bubble volumes. From the volumes, we can define a certain length scale, which is the equivalent radius here, as well as a velocity scale based on the assumption that the inertial effects are equal to the buoyancy effects of the bubble. So to check for the validity of these scales, for the diameter and velocity scale, we first plot the experimental bubble diameter as a function of the effective bubble diameter for the different fluids, which we can see first that the effective bubble diameter provides a good estimation of the experimental bubble diameter with an error margin of ±15%. For the low yield stress fluid, the diameter scale slightly underestimates the experimental bubble diameter. This is expected because bubbles rising in low yield stress fluid have an aspect ratio lower than 1. Similarly, for the fluids with high yield stress, the effective diameter slightly overestimates the experimental bubble diameter, and this is expected because experimentally the bubbles rising in high yield stress fluids have an aspect ratio larger than 1, so they are elongated in shape. It is also worth mentioning that this scaling law works for smaller bubbles produced by Lopez and al. So with bubbles of effective diameters between 0.02 and 0.05 meters. Okay, to check for the validity of the velocity scaling, U is equal to radical GR. We do the same thing. So we plot the velocity, the experimental bubble velocity as a function of the scaling velocity. We can see that this scaling velocity provides a good estimate of the experimental velocity with an error of around 20%. There's two significant interesting observations. First, that generally this scale velocity provides an overestimation of the real bubble frequency, real bubble velocities, and this is because the scaling law doesn't take into account any viscous effects, where in real life the viscous effects tend to resist the propagation of the bubble upward, further slightly reducing its velocity. And another interesting observation is that for fluid 3 with the highest yield stress, the experimental velocity is larger than the velocity scale. And this is because that for such high yield stress fluid, the preferential paths start to play a more important role. So preferential paths are the paths with minimum viscous resistances that develop in the fluid, and the gas will try to seep through them or with slippage. This is validated by experimental observations when we can see that these bubbles barely interact with the surrounding fluid indicating the presence of slippage. So in general, the bubble diameter scaling and the velocity scaling provide good order of magnitude of the experimental bubble characteristics. Finally, if I'm considering the bubble aspect ratios, so from experimental observations, we saw that the bubble aspect ratio is always a competition between inertial forces on one side and yield stress and viscous forces on the other side. So in general, bubbles with aspect ratios lower than 1, so with low aspect ratios are more desirable as they tend to induce more to shear a larger volume of the fluid around them and reduce the risk of tunneling. This is not a problem for a low yield stress fluid, as we can see that the aspect ratio is always around 1 or lower than 1. But for the high yield stress fluids, which are more representative of the industrial fluid, this is a problem because the aspect ratio produced at low injection flow rates are very high, of the order of 2.5, 2.7. So reaching aspect ratios lower than 1 is very hard for these fluids. We can set an aspect ratio, a maximum allowable aspect ratio of 1.5 here. So increasing the injection flow rate will drastically decrease the aspect ratio below acceptable values. So now finally we can try to plot the aspect ratio in the form of a dimensionless correlation. So we are plotting the aspect ratio of the bubble as a function of the Reynolds of the bubble over Yg of the bubble. So in fact, the physical meaning of this parameter here, it is the square of the inertial forces over the viscous forces and the yield stress forces. So we can see as this value increases, the aspect ratio will exponentially decrease to reach a minimum of around 0.75 when the Reynolds over Yg is equal to 500. After this value, it will slightly rise, tending toward a plateau around 1. We can also see here that the wall effects can be neglected, are minimal, and are only a little bit evident for the low yield stress, for the lowest yield stresses at highest injection flow rate. So finally, this evolution of the aspect ratio as a function of the Reynolds over Yg can be fitted into the following correlation with good agreement, with good accuracy. So in conclusion, we started by estimating the bubble frequency starting from accessible parameters or the dimensionless numbers of the liquid. So it appears that the bubble frequency is governed by the balance between inertial and buoyancy forces of the liquid. Having access to the bubble frequency allowed us to define scaling laws for the bubble diameter, bubble velocity scale, as well as a correlation for the bubble aspect ratio to estimate them in a non-dimensional manner. In the context of mixing, bubbles with larger bubbles are more desirable, high velocities are more desirable, and lower aspect ratios. So it is recommended, in fact, to increase the injection flow rate as much as possible, because the yield stress itself is an intrinsic property of the fluid, so I cannot change the yield stress. It's an intrinsic property of the process, so I cannot change the yield stress. Okay, concerning the liquid phase dynamics. So in the liquid phase dynamics, I just want to recall the three zones that are present in the reactor. So we have a rising fluid zone, which is the blue zone. We have a descending fluid zone, which is the green zone. This will create some kind of recirculation in the fluid. So we try to study this behavior using two methods. The first method, it aims at finding the average descending flow rate or average fluid downward flow rate. And this downward flow rate is always balanced by an upward flow rate due to the conservation of mass. And the second method aimed at finding the shape and the extent of the actively mixed region to define the mixed regions and the dead regions in the reactor. So we can start with the first method. The first method starts by injecting a colorant dye at HL/2 in the reactor, across the reactor. Then tracking the evolution of this line as a function of time for a certain duration tau d. After which, when I plot this evolution, I can finally estimate the average downward flow rate by performing an integration in the cylindrical system RZ theta. So I can finally find the average downward flow rate using this equation here. Okay, so I'll start by presenting the effects of the yield stress and the injection flow rate on QL. So the average fluid flow rate is now called the QL. I'll call it QL for easy. So as we increase the injection flow rate, QL will increase. This is in fact this is expected because increasing the flow rate will produce bubbles with lower aspect ratios, larger bubbles, and these will tend to agitate a larger quantity of the fluid around them. Whereas increasing the fluid yield stress tend to drastically lower the QL values, and this is expected because fluids with higher yield stresses are more resistant to flow. Concerning the effect of the tank size, so here we can see a QL as a function of flow rate for different tank sizes or tank width. We can see that the tank size is negligible at the first two injection flow rates. It's only here. It's only present at the largest injection flow rate. But keep in mind that the QL values by itself it's not a good representation of the quality of mixing. So in fact, I can because it doesn't take into account the total fluid present in the reactor to compare it to this QL. So we defined a dimensionless QL. It's called the QL star. It's the experimental fluid flow over a characteristic fluid flow. And finally, we tried to estimate this QL star in terms of the dimensionless numbers of the liquid phase. So we can see first that the most significant power here it's for the fluid yield stress, and for the fluid yield stress, so increasing the fluid yield stress will drastically decrease the QL star values. This also appears in the graph where we can see that the low yield stresses have values 1 order of magnitude larger than the high yield stresses. Okay, the second method it aims at finding the extent and the shape of the actively mixed region. So it starts by preparing of a colorant dye and spreading it across the free surface of the reactor. As time passes and injection commences, we track the colored region here as a function of time. Finally, we are able to estimate this mixed volume starting from the projections, from the 2D projections of this shape using this equation, this simple equation. So the final step will be normalizing this mixed volume by dividing it over the total volume and fitting it into the following exponential equation. So the graph here, it plots the evolution of the dimensionless mixing volume for the same fluid at 3 injection flow rate. So this is a low yield stress fluid. So in fact, this correlation, we have two main parameters. IM it represents the maximum mixed ratio. Here the arrows indicate that the trend of in IM as a function of increasing the fluid yield stress or the injection flow rate or increasing the tank width. A red color means an undesirable effect. A green color means a desirable effect. So IM it represents the maximum volume that could be mixed as time tends to infinity. The second parameter is tau m. Tau m, it's a characteristic time of mixing. So we can assume that IM is reached after 3 tau, and the arrows the same way that represent the trends in tau m as a function of changing the experimental variables. So in fact, we can see that the increasing of the injection flow rate leads to a desirable effect in both the value of IM and the value of the mixing period, whereas increasing the tank width or decreasing the aspect ratio of the reactor leads to adverse effects on both parameters. So after that, we tried just expressing IM, which is dimensionless by nature, and as a function of the dimensionless numbers that represent the liquid phase. So we can see that the aspect ratio of the reactor plays the the largest role. So increasing the aspect ratio will increase the value of IM, whereas the Reynolds or the inertia and the yield stress plays equal but opposite effects on IM. So increasing the inertia will increase IM, increasing the yield stress will decrease IM. The final step was finding the circulation time, the final step was using a cross-validation between the two methods in order to find an average circulation time or an order of magnitude of the circulation time, which is the time needed for a particle to do a full circulation in the reactor. So we started by defining a descending velocity and a rising velocity based on the QL value and the cross-sectional surfaces. From these velocities, we can define a descending time and a rising time. So the circulation time can be estimated as the time needed for descent plus the time needed for rising. We can see that the circulation time is a function of R2 squared. R2 is the extent of the yielded region at HL over 2. If we assume an axisymmetric flow, and if we assume also that the shape of the mixed volume as a semi-ellipsoidal shape, so we can write the function that describes this extent of the actively mixed region. Finally, we can find R infinity as a function of the volume mixed and HL. So we can find R infinity. We can substitute it in the equation of the semi-ellipsoid here, and we can finally find R2 squared. So I'll not go into details, but we can finally find R2 squared in terms of non-parameters, and we can finally find an estimation of the circulation time as such. So we tried a cross-validation by plotting the 3 tau m that comes from the extent of the yielded, that comes from the extent and the shape of the yielded region from method 2 as a function of tau c, the circulation time, which comes from the QVL method. And we can see that we have a good agreement between the two, with a plus minus 25% error, which is expected given the simplicity of the model here. So in fact, so we can see that for the circulation time, increasing the volume mixed will increase the circulation time, and increasing the fluid flow rate will decrease the circulation time needed. So in conclusion, we studied the liquid dynamics using two methods. The first method finds the average fluid downward flow rate. We produced also a correlation for that. The second method defines the actively mixed ratio IM with a correlation for that. Then we used the both methods in a cross-validation process to find an order of magnitude of the circulation time in the reactor. In the context of mixing, it's recommended to work with tanks with high aspect ratios and high injection flow rates. The results of this chapter were also a subject of a submission in American Institute of Chemical Engineering, a journal. Okay. Part 4. So now I finished the experimental part. I can see from the experimental part that there are still quantities that are missing or inaccessible, such as the local fluid velocities. So we try to develop a numerical model to tackle this problem. So the numerical model was built using OpenFOAM, which is an open source software that allows the solution of CFD problems. ParaView was also used for data visualization and post-processing. So in general terms, the model considered the VOF method, the volume of fluid method, with a 3D dynamic mesh as well. So we considered 6 cases, 2 fluids, a low yield stress and a high yield stress, and 3 flow rate in each case. So the governing equations of the VOF method are mainly summarized by the continuity equation in its incompressible form, the momentum conservation equation, and the phase fraction transfer function. The fluid, concerning the fluid modeling, in fact, we modeled the gas that is injected as a Newtonian gas, whereas the liquid that's present in the reactor is modeled as a regularized Hojeij model. So it's a biviscous model. This model assumes the presence of a certain critical shear rate called here gamma dot C, which is equal to the yield stress over the creeping viscosity at 0. So below this critical shear rate, the fluid will tend to behave like a Newtonian fluid with very high viscosity. Above this critical shear rate, the fluid will tend to behave, will follow the normal Herschel-Berkeley behavior. This is done just to get rid of the discontinuity at 0 and the problems it introduced to the numerical solver. So it's very important to choose an eta 0 creeping viscosity as large as possible, as large as numerically possible. So the natural first step was doing a creeping viscosity sensitivity analysis. So here we are plotting the bubble diameter and the bubble frequency as a function of the creeping viscosity value. So it's eta 0 over rho. We can finally see that we reach almost a plateau for an eta 0 equal to 1 million Pascal seconds. So we chose this value because it provided the most accurate result with acceptable computational cost, of course, and stability, keeping the solver also stable. Similarly for the mesh, we performed mesh sensitivity analysis. So the graph here, it plots the evolution of the bubble frequency, diameter, and height as a function of the initial number of cells that are present in the mesh. So we can see that we almost reached a plateau for initial number of cells of around 8.8 times 10 to the power 5 cells. So we chose this as the initial number of cells. So in fact, as a summary of the mesh, in fact, the mesh have initial number of cells of 8.8 times 10 to the power 5 with a maximum cell spacing of 0.5 centimeter. But in fact, the mesh itself is a dynamic mesh, and we have a refinement and the interface to increase to decrease this delta x at the interface, and better capture the interface and reduce the inherent diffusivity of the VOF model. Concerning the computational costs, so each case was parallelized on 128 cores, generally to simulate 1 second of the flow. 6,400 core hours of computational time are needed. This is an order of magnitude. In fact, it changes depending on the injection flow rate that we consider and the fluid rheology. So we considered 6 cases. Each case took around 1 week to complete 3 seconds of the simulation, something like that. Okay, the video in fact shows a sample result of the numerical simulation. Okay, so we can start by qualitative validation of the model, so by visual validation. So the table here, it plots the experimental observations or the experimental result of the bubble shapes compared with the respective numerical observations for different Reynolds numbers. So we can see there's a good agreement just from visually examining the figure. There's a good agreement between experimental and numerical results. In a quantitative validation, the 3 plots are simple. They show the bubble frequency, the bubble diameter, and the bubble velocities that are produced both experimentally and numerically. We can conclude that the model, in fact, model the gaseous phase to a high degree of accuracy with 11% error in the bubble frequency with respect to the experimental case, 17% error of bubble diameter with respect to the experimental case, and 20% error in the bubble velocity with respect to the experimental case. Okay, now concerning the liquid phase, we can try to simulate the 2 methods that we performed experimentally by performing Lagrangian particle tracking. So this Lagrangian particle tracking, in fact, it is a post-processing step. Here concerning the QVL method, we have 2 results: the one produced from the Lagrangian particle tracking or the numerical result, and the experimental result from the QVL method. And we can see there's a good agreement between the 2 results, between the numerical and the experimental result. We can also perform Lagrangian particle tracking by placing a line of particles at the free surface of the fluid and tracking the evolution of this particle as a function of time. Even if the simulation duration is short, which is 3 seconds, we can assume that the velocity field is periodic and simulate the flow for larger amounts of time. So finally, here we can see a comparison between an experimental result and a numerical result found by Lagrangian particle tracking. So I just finally need to mention that the results of the numerical model was a subject of an accepted publication in American Institute of Chemical Engineering journal as well. So finally, conclusions and perspectives. So I'll just mention the final conclusions. First, concerning the gas cavity, we concluded, in fact, that the gas cavity is more or less a local phenomena with minimal effect on the overall mixing of the reactor. So the gas cavity can be neglected with respect to the mixing of the fluid in the reactor. Concerning the gas bubbles, in fact, the bubble frequency, the bubble diameter, and the bubble rising velocities are governed by the balance between inertial and buoyancy forces of the liquid. The aspect ratios are mainly governed by a competition between inertial forces on one side and yield stress and viscous forces on the other side, with minimal effects of the wall. So finally, larger aspect ratios and larger bubbles are recommended. So it's recommended to work on a high injection flow rate. Concerning the liquid phase, in fact, the mixed ratio IM and the circulation time IM TC are mainly affected by the aspect ratio of the reactor, the liquid viscosity, and the injection flow rate. So it is recommended to work on high aspect ratios of the liquid and the highest possible injection flow rate. So here finally we try to use the correlations that we produced just to get orders of magnitude of certain flow characteristic in an industrial case reactor. So we consider here a 200 meter cube reactor with 10 compartments. This will make a single compartment of around 10 meter cube. So a single compartment of 10 meter cube. We also consider the following fluids that range in yield stress from 68 pascals up to around 1,000 pascals, and these fluids were taken from a previous PhD that, in fact, so they resemble the rheology of the real fluids present used in the industry. Applying the correlations that we used, we were able to find an order of magnitude or an estimate of the maximum mixed volume IM, the circulation time TC, as well as the third characteristic here, which is called D star infinity. So D star infinity, it represents the ratio between the extent of the mixed region and the width of the reactor. So when you have D star infinity less than 1, it means that the compartments are not interacting with each other. And when you have a D star infinity larger than 1, it means that the different compartments are interacting with each other. So as you can see, these colorations present an operational tool for roughly estimating key flow parameters and can be used in the preliminary stages of designing such reactors. Okay, perspectives. The study can be further developed experimentally and numerically. So experimentally, in our case, we fixed the liquid height. In fact, it is interesting to take liquid height effect into account and how does the liquid height will affect the shape and the extent of the yielded region in the reactor, as well as the flow trajectories. It is also it's also interesting to take the pipe configuration into account. So, for example, doing an injection at HL/2 and checking how does this injection change the flow profile inside the reactor. For example, we can also consider multiple injection points to test for the interaction between multiple injection points and try to finally find an optimal spacing between the pipes that can be used. Finally, we can also work with liquid suspensions by considering buoyant particles dispersed inside the fluid. So the idea of this, that the buoyant particles, when the injection stops, the buoyant particles would tend to rise toward the free surface, creating a segregation in the liquid phase. This will allow us to finally define an optimal duration between two injection cycles, for example, to prevent this separation. Okay, from a numerical point of view, in fact, the numerical model can be further utilized in many ways. First, the geometry can be easily modified, so the reactor dimensions, the pipe and the pipe dimensions can be easily modified. The initial condition can also be easily modified, so the injection flow rate as well as the fluid rheology can be modified directly. The numerical model finally, which is the main goal of the numerical model, was it allows us to access inaccessible parameters experimentally. For example, the velocity field evolution, as we see in the video, which is the local velocities that are present in the liquid as a function of time. It also allows us to define the shear rate map starting from the second invariant of the velocity field, and the evolution of this shear rate map as a function of time. We can also perform Lagrangian particle tracking to find average liquid kinetic energy or average power input into the reactor. We can also calculate an average velocity, average phase velocity, which is the velocity over all the points, over all the time steps, to get a quantity that represents the liquid flow in the reactor. And thank you.
Merci beaucoup pour cette présentation exhaustive et
Yes, I speak a little bit fast.
Mais merci pour la présentation, c'est exhaustif et ça prend en compte certaines recommandations de vos rapporteurs. You take into account some recommendations by the review presentation today, right?
Yes.
Okay, thank you. Donc la parole pour le premier rapporteur, donc professeur Ouazili de Nancy, s'il vous plaît.
Merci, Monsieur le Président. Vous m'entendez bien?
Parfait.
Super. Donc, je vais commencer par remercier Laurent et Philippe de m'avoir invité dans ce jury de thèse qui est extrêmement intéressante comme thèse. Et je ne sais pas, je dois continuer en français ou bien switcher en anglais.
Pour maintenant, c'est bon.
C'est bon, très bien, entendu. Donc, ensuite, je voudrais féliciter sincèrement le doctorant, donc Ali, pour la présentation qui est très claire, même si effectivement qui suit le plan de la thèse manuscrite, et tout en ajoutant quelques nouveaux résultats pour éclaircir davantage la ligne conductrice présentée dans le manuscrit de la thèse. Et ensuite, je voudrais le féliciter sincèrement pour à la fois la quantité et la qualité des travaux réalisés, puisque vous êtes engagé à la fois dans l'expérimentation difficile avec un fluide à seuil qui n'est pas facile à manipuler, ensuite en injectant une phase gazeuse, et puis ensuite vous êtes aussi engagé dans une simulation numérique, donc avec un code open source, open form, bien entendu, qui nécessite cette maîtrise aussi. Donc, dans la thèse présentée, il y a beaucoup de résultats à la fois expérimentaux que numériques, que j'apprécie beaucoup personnellement. D'autant plus, effectivement, mon équipe travaille un peu dans le domaine à des flux non newtoniens, pas jusqu'à seuil. Donc, je vais jouer un petit peu le rôle de rapporteur pour poser quelques questions. Donc, première question qui revient à l'esprit, bien entendu. C'est une question facile sur la propriété rhéologique du fluide carbopole. Donc, pour la cavité de gaz, pour la bulle, etc., vous utilisez des fluides de carbopole à différentes concentrations. Et dans chaque chapitre, effectivement, les propriétés rhéologiques telles que contrainte seuil et consistance, l'indice de l'écoulement, etc., changent un petit peu pour une concentration donnée, 1% par an. Je comprends bien, effectivement, quand vous mélangez le fluide, il y a toujours un peu de poudre de carbopole collé à la paroi, à l'agitateur, etc. Néanmoins, il y a beaucoup de différences, ne serait-ce que pour une contrainte seuil. Quelle est l'explication dans ce cas-là pour cette variation des propriétés rhéologiques?
The idea is that, in fact, we cannot specifically control the yield stress that we need. So we start by a concentration, taking it was taken from a graph by GM Pau, an article. So it relates the concentration of the carbopole as a function of the produced or the expected yield stress, but in fact it is not straightforward because there is some dispersion for the yield stress. So sometimes working with the same concentration, if the batch is different, you might get a different yield stress. I think also that the fluids that were prepared in the first chapter were only prepared 10 liters, so we only prepared around 10 liters of the fluid. When we worked with the other chapters, we in fact prepared like batches of 90 liters. So probably the method of preparation is a little bit different from here to here. So
certainly.
It would induce some difference in the expected yield stress. So
okay, I understand where. Yeah. Okay.
Okay.
Thank you for the response. Of course, yeah, I understand. Okay. So when the concentration of polymer is quite slightly different in time.
Yes.
Between different experiments. Yeah. Okay.
It is because the quantities change from 10 liters that can be fully agitated and easy up to 90 liters. I think the method of preparation here is a little bit different. It affects the carbopol yield stress. It's also that in the first article we worked with an old batch of carbopol powder. So in the second and the previous and the after articles we had a new batch of
certainly the powder can be stick to the wall to the stereo.
Something like that will slightly change the and even in the graph it's not really straightforward that each concentration will have an exact yield stress. So in fact the graph is plotted in a log scale, so you can see some dispersion, and in the log scale a small dispersion means probably 20% sometimes in change of things.
Concentration of the powder is homogeneously dispersed in the liquid anyway.
Yes.
Okay. And the second question concerning always the rheological properties. For example, carbopol is not only a yield stress fluid, but also a thixotropic fluid, as you mentioned in your thesis also. And the thixotropic properties means that the property can vary over the time. When you inject the gas cavity followed by bubble formation, for example, in this case, you determine not only the cavity size, bubble size, but also the formation frequency. And how is the effect of the thixotropic property on the frequency, for example?
In fact, I didn't. In fact, I didn't understand well the question.
Okay. The properties of the carbopol solutions display thixotropic properties.
Yes.
That means the time varying properties.
Yes.
When you inject consecutively some bubbles in time, do you check the property evolution of the thixotropy or not?
I mean, do I do the rheological characterization regularly after each?
Yeah.
No, in fact,
at the beginning of at the beginning of your experiments, you injected the first cavity or the first bubble.
Yes.
Maybe the viscosity will be higher, or the shear stress will be very high.
Yes, in fact, there is some history effects that always remain in the carbopol, but in fact, we didn't check for that because the typical duration of the experiment is, for example, in the order of seconds up to the order of minutes. Okay, and we try to do multiple trails in the same day. In fact, for the rheological characterization, I always measure tau 0, k, and n. So we don't always do the frequency sweep and the amplitude sweep test. Okay. So I think also, as you said, this thixotropy will induce some errors. In fact, some accumulative errors as time passes. But I don't think like from the flow that we are considering, it is the inertia that is always trying to dominate the flow. The inertia of the gas that's trying to dominate
the inertia is okay. It's imposed by the gas flow.
Yes.
Yeah. But however, for the liquid phase, in this case, at the beginning of the experiments, at the end of the experiments, is there some deviation of the rheological properties?
There is small deviations, but it is always negligible. So it's between 5% plus minus 5%. And I think this is on when doing a rheological characterization of a sample where I make sure that for example, there's no bubbles inside it, entrapped bubbles inside it. But if you look at it on the grand scale, the bulk scale, especially for the high yield stress fluids, that as time passes, in fact, bubbles will try to get stuck inside the fluid, making it a little bit less viscous, if you might say, because it becomes like a sponge. So in fact, we need to wait for another day for some bubbles to get released, but there's always some bubbles that remain stuck in the fluid, and it becomes more blurry.
Okay. So we think the influence of the time changing property.
Yes, this might have some influence, but in fact, we can only test them by using the rheometer or using a small sample with no bubbles, and we can see that the change is minimal. It's only around 5% after using the fluid for several experiments. And the idea is that because of the large number of the trails that we did, and preparing a rheological solution cannot be in 2 hours. So in fact, you need 2 days to prepare a rheological solution. And the idea is that if the first time I prepare a rheological solution with tau 0, k, and n values, if I aim next time for the same values, I cannot find them. I cannot get the same values, which makes comparison of each effect, for example, inertial effect, and independently is very hard, because all of the parameters are always changing between a trail and the other.
Okay. So I will continue with some questions relating to the configuration of the injector pipers. As you show in your introduction today in your oral presentation, usually the majority in industrial cases, the configuration of the injector tubes is of upward configuration, upward, because you should intensify the Beyonce force impact. And in your case, I noticed also in the industrial configuration in Arcolia, for example, you use the downward configuration. The gas cavity is injected downward. And why you choose this configuration, downward injection?
So in fact, to start with, I start by considering the industrial case, and we study it. You're right that most of them, they use upward injection, but I think Arcolia used downward injection because if you have a thick fluid and you are ejecting upwards, you have a more probability to develop a tunneling effect. And you can see a tunneling effect happens when you get a tunnel of gas or a pipe of gas across the liquid, and the liquid will not be affected at all. Just the gas will get released upward. But in fact, our focus was made on the geometry that is present in the industry. Okay, so we could have, for example, studied the upward injection compared to the downward injection, but that was not the scope. Yes.
Okay. In the industrial configuration, they use the downward injection in Arcolia, for example. I noticed in the 200 meter cubes anaerobic digesters in the industrial. Okay. You want to accumulate some gas volume, in fact.
Yes. Yes, probably right. I think it's also because of they are trying to remove any substrate that is accumulated at the bottom. So this will probably help in cleaning up the floor of the reactor. But this is
you want to increase the bubble volume, in fact, so you can intensify to some extent the rising velocity and the mixing volume and so on. Okay, but as you change also the injector diameter from 2 millimeters until to 10 millimeters, for example. So for giving gas flow rates with different orifice, of course, you can increase decrease the cavity volume.
Yes.
You can control also this parameter. Next question relating the downward injectors configuration. For example, the presence of the injector pipe affects largely the rise of your bubbles. In fact, because it's in your manuscript of thesis and also in your presentation today, we can see the bubbles during their rising trajectories. The bubbles are still attached to the injector pipes. So the dysmetria of the bubbles is enhanced.
Okay. I thought I understood the question. The idea is that you mean that the characteristic of the injection bubble of the injection pipe itself will affect. Yes, in fact, it will affect it. It will depend on the cohesion forces probably between. So if for example we had a hydrophobic property of the pipe, I think this might increase the risk of tunneling. So the gas will try to separate the liquid from the pipe and create a certain tunnel. But as you can see in all of our study, we always neglected the effects of the bond number or the effect of the surface tension. So because in fact we have multiple effects to take into account, we were we stopped with these effects, which are the inertial effects, the viscous effects, and the geometry of the reactor effects. I'm not sure if I really answered your question because.
Yeah, just the presence of the injector pipes, in fact, attached bubbles during their rise. In this case, the rise bubbles is not free rising, in fact, because bubbles sliding on the pipe tube surface.
Yes. So I think
maybe the rising velocity will be slowed down with respect to a free rising bubble.
Yes. So in fact, you can see in fact from the scaling law that we devised, the real experimental velocities were a little bit lower than the scale velocity. So the experimental velocity was lower than the scale velocity. We tried to explain that by the effect of the viscous effects, in fact, because they tend to decrease the velocity. But as you can say, probably also because the bubble is also attached to the injection pipe, it also tends as a resistive force on the bubble velocity. So it also contributes to the decrease in the bubble velocity. But even then, with our results, the velocity scale it's accurate with an error margin of 20%, plus minus 20%. So it's somewhat acceptable. But yes, because the bubbles are attached to the injection pipe, this might decrease the rising velocity if I'm comparing it with a free-flowing bubble velocity, like in an infinite medium, and the bubble is rising with no pipe. Yes.
Okay, I see. So in your mixing volume of mixing time measured experiment by the color meters was a dies.
Yes.
For the mix time, especially you use the one line tracing, and for the mixing volume, you use volume tracing, of course. And again, you use some axisymmetric assumptions, of course, for the bubble. I understand well. It's a difficult experiment, but in fact, your bubble is not only dysymmetrical, of course. Signally, due to the presence of inject pipes, of course, as the bubble is attached to the rising in the inject pipes, the dysmetry is more pronounced. So how is the deviation due to the simplification of axisymmetry in your estimation?
Okay. Yeah. So the idea is that we started with this method considering only one reactor, which was the smallest reactor. Okay, and when we considered one reactor, we had two cameras. We had one camera facing the reactor and the other camera on the other side. So in fact, we were treating it as not axisymmetrical for the mixing volume method. Okay, so when we finally estimated the volume, we took so AXY, which is the projection on AXY was different than AYZ. Okay, it was slightly different, but when you are estimating this volume, in fact, it is the equation itself is an estimation of the volume. The equation itself, even if I'm having on both planes, I'm having some errors of estimation. So the estimation, the equation is perfect when you have a convex shape with no concavities, with no concave.
Okay. Thanks for this accuracy. Okay.
Yes,
You made use, in fact, of 2 cameras.
Yes, in fact, I had a camera and a mirror to see the other side and to prevent it
perpendicular way. Okay.
Yes, to have the same this view and that view at the same instant of time, and I tracked the both of them. The change is not so there is a change, but the change is not very evident, and because of the logistic difficulty of this, when we considered further tanks, larger tanks, we neglected the other cameras, so we only had a single camera and performed on a single one.
Okay, based on the color volume that you measured with 2 cameras, and they use an approximation of ellipsoid.
No, yes, no. First, we can
reduce, for example, for the mixing area.
I'm talking about the estimation of the mixed volume VM. Okay, if you remember that VM is estimated as a radical AXY squared times AYZ squared times the projection from the top. Okay, so if you consider these 3 planes, you'll get an estimation, and if you consider only one plane and assume that the other plane is symmetrical to this one, you'll get a very close estimation of the volume. So there's no very large change. There is a change, but it's not very large, and it's really technically difficult and time-consuming to consider each time the 3 cameras together.
Okay,
that's why,
I see. Yeah.
Okay, so this is different.
Yeah, I understand. Okay, thanks for the reply. In this case, for the mixing volume, mixing time, of course, you use a first-order equation to describe. For example, you use the exponential equation to describe the mixing time. Yeah. So that's, you suppose the total volume is mixed by the assumption of bubbles. Because in the Reynolds number, liquid Reynolds number, you use the width of your channel, for example, WT, as a characteristic length.
Yes.
Yes.
No, I didn't get the question, really. I didn't get the question, really.
Okay, I will repeat. In the mixing section for the liquid phase flow.
Yes, and the extent and shape of the mixed region. So the second method. Okay.
You made the use of a Reynolds liquid number, for example, based on the width of your reactor, in fact.
Yes.
And when you use the width, so WT, for example, as the characteristic length, that means implicitly that whole volume of the liquid is mixed.
No, in fact, no, in fact, I represents the ratio of the volume mixed over the total volume. So we don't have a case where all the total volume is mixed. Okay, we get something very close to that when we have only at the corners, no mixing. But
okay, I see. Because today you show where there are 3 distinct.
In fact, I said
rising zone and a sinking zone, downflow zone of liquid, and of course you have third stagnant zone also.
Yes. The idea is that if we are considering a low yield distress fluid, a significantly low yield distress fluid, and a small reactor, the shape will try to deviate a little bit than the typical ellipsoidal shape. So it will be a rectangular shape at the bottom and at the top, and then it will tend to close to connect into the points at which the injection is happening. So you'll get something like slightly different than ellipsoidal shape.
Okay, je ne vais pas monopoliser la parole. Now I will go ahead to the numerical simulation part, CFD part, of course, yeah. you use the OpenFOAM as a software to simulate
Yes.
the bubble rising. And how is the CPU time? There's no detail in your manuscript. What is the CPU time, CPU computing time?
The CPU,
Yeah.
it was not in the manuscript, but I added it here in the presentation. So in fact, each case was parallelized over 128 cores, okay? And I put some computational costs. So in fact, to simulate a single second of the flow, it was around 6,400 core hours of computation. In fact, this computational cost is not really specific, but it's an order of magnitude, because as you change the injection flow rate, this will change a little bit, or as you change the fluid yield stress, this will change a little bit. The idea is that the delta T that we choose, it's not constant. So the time step is not constant. It's always calculated based on the current number. So we set a current number of less than 0.75 and an interface current number less than 0.5. And based on that, the time step is always recalculated.
So for a typical example for computation, it will take about 6,000 hours.
Yes.
CPU. Okay.
So generally, to simulate one case with one flow rate and one yield stress for 3 seconds, it will take around a week of simulation. Give or take.
Yeah, I noticed that you use a relatively bigger cell size, so computation
yes,
is
concerning the numerical simulation, I think this performance can be further developed by doing a deeper study on the mesh. So we can probably optimize the mesh, especially because we use
certainly you use in fact bigger mesh size.
Yes. So in fact we can in fact use like a larger spacing in the bulk of the fluid, especially if we are considering a high yield stress fluid, because we know that the velocities, the order of the velocity is low, with more refined around the injection pipe, which is the main region where the bubbles are rising, as well as the walls. So if we try to optimize the mesh, we can improve the computation efficiency of the model.
Okay, I understand. Another question for the CFD, for example, you certainly use the critical yield shear rate to distinguish the stagnant zone and the motion zone.
Yes.
But in your VOF scheme, you use the viscosity weighting, a linear with viscosity weighting.
Yes.
This weighting assumption is not always valid, even for Newtonian fluids. How is the possible effect with a non-Newtonian fluid, such as a carbon pole?
So in fact, the Hojeij-Buckley model, it's already pre-programmed in OpenFOAM. The idea is that because you have a certain discontinuity at zero, at gamma is equal to 0, this will induce many numerical problems. So what the program tends to do is that we can consider a very high viscosity in this small region to get an almost vertical line. So it's not a vertical, it's an almost vertical line. And after this critical shear rate, it will follow the normal Hojeij-Buckley model. Because we cannot really simulate a Hojeij-Buckley model numerically without solving the problem of the discontinuity around 0.
Okay.
Okay.
Je vais pas monopoliser la parole. Last question, always about the CFD results. Some numerical results display a very high shear rates, for example, even above 100 up to 10,000 per second. In experiment in the industrial configuration, of course, the shear rate is much lower, typically around 20, 30 per second. So why this strange?
In fact, because the shear rate map, the VOF method doesn't differentiate between a gas or a liquid, so it tries it always considers all cells as a mixture, and depending on alpha, it chooses as a liquid or a gas. Because in fact, the shear rates inside the gas itself, because we have a very high gas velocities. So the gas velocities inside the pipe are starting from 13.7 up to 54 meters per second. So they appear very large. And I get your point. So the range is very large. It can be easily reduced. So it's just a post-processing step. It's just changing the legend or the color map, and it will be good. It will be fixed. So
okay, I see. I see. So I came before in your lab. I know in your lab you have a PIV device, particle image velocimeter. During your thesis, did you try to use?
Yes, but trying a PIV for such large reactor with such depth and the clarity is not very. So the clarity is not perfect for carbopore, especially after you use it. So it was almost impossible to try to do that. In fact, the PIV will only consider a plane of the flow, right?
Yeah.
And we can see that yes, assuming that it is axisymmetric, but it's not axisymmetric. And also the clarity was the main point. The clarity was the main issue.
Okay, thank you very much, and congratulations again. Merci beaucoup, Monsieur le Président. J'ai terminé mes questions. Alors. Merci beaucoup.
Merci à vous. Merci à vous. Donc, Monsieur le professeur Cox, vous avez la parole.
Oui, merci, Monsieur le Président. Est-ce que vous m'entendez bien?
Très bien.
OK. Donc, je voudrais remercier également Laurent et Philippe de m'avoir invité à ce jury sur un sujet qui est assez original, très original. Donc, avec effectivement un travail qui est assez intéressant au niveau qualitatif, puisqu'il y a énormément d'expériences qui ont été menées. Et puis après, une petite analyse avec un outil numérique qui permet de compléter ce travail de thèse qui est un très beau travail dans son ensemble. Donc, je voulais aussi féliciter Ali pour ce très bel exposé qui était d'une bonne qualité pédagogique. J'ai trouvé ça très clair. Bon, le débit était un petit peu rapide, hein, mais peut-être que c'est l'effet de la distance qui accélère le débit, je ne sais pas. En tout cas, j'ai bien apprécié les slides, hein, très clairs, avec un effort de synthèse par rapport au manuscrit, avec des rajouts, effectivement, qui ont tenu compte de nos petites remarques en termes de regroupement d'informations, par exemple la présentation des nombres adimensionnels avec un effort de synthèse. Voilà, et puis une analyse un petit peu plus phénoménologique aussi, rassemblée également via des slides qui, à mon avis, sont très utiles aussi en complément de la thèse. Voilà, donc je vais jouer maintenant un petit peu mon rôle de rapporteur. Je vais juste revenir sur ce que j'ai écrit dans le rapport de manière très globale. C'est vrai que je pense que dans ce travail de thèse qui est présenté sous forme de publication, donc c'est intéressant parce que ça a permis de valoriser le travail en temps réel, il y a besoin quand même d'avoir des annexes avec les résultats expérimentaux en dimension réelle pour que la communauté scientifique puisse s'appuyer sur ces résultats expérimentaux très innovants et éventuellement faire des comparaisons à la simulation numérique. La présentation des résultats sous format dimensionnel est intéressante pour produire des corrélations, mais rend parfois difficile la comparaison même entre chapitres. Voilà, donc je pense que c'est utile de rajouter des annexes, bon, dans la mesure du possible. Hein, je ne sais pas quelles sont vos disponibilités, mais dans la mesure du possible pour donner un petit peu plus d'utilité à moyen terme en fait à ce travail. Voilà, donc maintenant, je vais passer aux questions. C'est bon en français pour les questions?
Oui.
OK, si ça ne va pas…
Or in English, it will be better for me in English if you can.
OK. So my first question concerns the hydrodynamic part. When you present some results about the frequency, can you explain how do you measure the frequency from your experimental data?
Okay.
It's not explained in details in your publication.
Yes. So the idea is that the frequency of the cavity frequency or the bubble frequency.
for example, the cavity frequency.
Okay, for the cavity frequency, we can see at the injection point the limits of the cavity. So the limits of the cavity will tend to expand, then collapse, expand, then collapse. So each cycle is considered as I say as a one cavity. Okay, so after that I count, for example, for 30 cavities and divide by the total duration that I have. So I'll get a frequency, a typical frequency of the cavity. Remember that, in fact, for the cavity, it's barely that you will get a time where the injection point is all filled with fluid. So there's always a connection of gas at the injection point. But the cavity frequency is mainly considered that the time needed or how many cycles during 1 second that the limits of the cavity diameter expand, then collapse. Okay, is it clear?
Yes.
So
when you calculate the frequency, you need some statistical convergence to have an accurate.
I do an average. Yes.
Yes.
No. I do
take just the maximum of the signal, and
no, not maximum of the signal. It's mainly when the direction of the movement of the interface changes. So the interface starts by increasing, which means the cavity is growing. Then it reaches a point, then start to decrease. Okay, so when it decreases, this is the first cycle.
So you have you can have a number of periods. So you measure the periods, and how many periods do you measure to do the average?
In fact, I generally do 30 periods, and I divide it over the duration.
Okay,
of the 30 periods.
Is it the same numerically?
For the cavity, in fact, we didn't really estimate. We neglected, so we didn't do the measurements for the cavity. For the bubble, it is close, so it's around. I think there's a 17% error between the two, and I think this is because of the diffusivity of the VOF model. So this is a numerical case, and this is an experimental case. But for the cavity, we were in a point in the work that it's clear that we can neglect the cavity. It doesn't really affect the dynamics of the overall mixing. That's why when we consider the numerical case, we neglected studying the cavity. So we focused on the bubbles and on the liquid, on how can we exploit more the numerical model for characterizing the liquid.
Okay, I have another question. It's about the bubble velocity. Can you go back to the slide 14, please?
Okay. 14?
Yes.
Yes. Okay, just. Okay.
So it's a question about the second graph. So I agree that you can use the scale velocity as the square of the gravity and the radius to build dimensionless numbers, for example. But in general, for large bubbles, we use to estimate the bubble velocity the Taylor and Davis relation, which is close to that, but you have a coefficient around 0.66 before the square. So if you put the relation of Davis and Taylor, which is given in several books like Clift, Kress, and Weber, you have a slope not with 1, but with 0.66.
Yes.
So can you comment why do you not compare with this relation? Is there a reason or
no? It's just I just known about that. So in fact, I don't know that there is a correlation. The idea is that even for the factor that we need to add, is this the factor for a Newtonian fluid or for bubbles in non-Newtonian fluid?
In this relation, there is no Newtonian effect because it's just inertia effect.
But from where does the factor comes? It's like a corrective factor. right?
No,
For
it's
the
not a
scale.
corrective factor. It's an analytical solution given by Davis and Taylor more than 50 years ago. And I think you can use it in non-Newtonian fluid also. So do you try to compare the results with this kind of relation?
No, not really. Not really. But I think it will create something even more closer to the experimental one. So because
Yes,
you can see that this scaling it overestimates by around 20%.
it's more often used for spherical caps bubbles, but it seems that it works also good in this case.
Yeah.
Your results are in between the two models, in fact, so it can be interesting to compare to this relation. So now I have other question on the mixing.
Yes.
So can you go to the slide 18, please?
18?
Yes, for example.
This one?
Yes,
Okay.
so I think you explained that you use the door-round pipe, and you explained that it's better for mixing, but I don't know exact why it's better for mixing. You explained some.
Which one?
With the door-round pipe, why it's better for the mixing?
For the downward pipe?
Yes. Why is it better for the mixing with this kind of gas injection?
As we previously discussed, it's probably because we need larger bubbles. So this configuration will give some time for the bubble. So will give some time for the bubble to reach a larger volume. It's probably, but here in this slide, I didn't mention that the downward injection is better for me.
I agree. Okay.
Yes, but I think because when performing a downward injection, so the bubble will spend a slightly longer time, like hold by the yield stress around it to inflate a little more. So it just gives brief larger time for the bubble to reach a larger volume of the bubble, rather than upward injection. Because in the upward injection, you see that in fact the inertia, the high inertia of the gas will act upward along with the buoyancy. So it will somewhat create like a jet effect upward. And if it creates a jet effect, so here I'm thinking aloud. If it creates a jet effect, the fluid here it becomes like a tunnel. So the fluid at this around this jet will not be really fully agitated.
Okay, so if you go back to the model of the mixing after the slides.
Mixing, yeah, mixing time.
Yes, the mixing time. Yes, for example.
Yes, so this is a very simplified model, but yes. Okay.
Yes.
Yes.
Yes. So in this model, the downward configuration, what does it change in this model, do you think, in this final model of the circulation time?
The downward configuration.
Does it change the liquid flow rate, or does it change the mixed volume, or the both?
If I consider upward flow rate, I think it will change both. In fact, we need to try it to be sure, but from the experimental observations that we tried, in fact, the limit of this fixed volume here, it's not the bottom of the tank, but it's rather at the point where the bubble is detaching.
Yes. Okay.
Okay. So when you get an injection, an upward injection, you'll create a jet, some jet, and the bubble will detach somewhere higher. So I think you will create a dead zone at the bottom.
Okay. I have another question about this flow configuration. The model that you present, in fact, is really close to the mixed volume divided by the flow rate. So it's normal to have this circulation
Yes.
time.
So in fact, from all this, we only get some factor here, some corrective factor, which is 9/8. But in fact, it is very simplified. So here, first, I'm assuming that the trajectory that is covered by a particle is upward HL, then downward HL. So it is somewhat upward then downward. But the real trajectory is it's not as this simple. So you can say first it is an oval shape, but also around the bubble you can see some small eddies, some small circular eddies.
But I agree with the result, but I think it's not 9 divided by 8. I think it's more close than to 1, because that's the real situation, because it's a closed reactor, so you can 1. But I have another question. Do you try to do the same kind of experiments with a Newtonian fluid? Because in the non-Newtonian fluid, on your graph, you can observe that the section S1 is smaller than the section S2. It's probably due to the yield stress of the fluid.
Stress. Yeah, the yield stress.
In the case of the Newtonian fluid, do you try to do the experiments reference?
No. I have. So the idea for the Newtonian case, we only have the one with the small tank, because having 90 liters of glucose is a logistical hazard. But for the small tank, I saw for the Newtonian case that in fact the shape will deviate from the ellipse shape. It will probably become a straight line along the walls. Then near the corners of the reactor, it is closed. So it will be a shape close to a rectangle. Then so the shape will change, in fact, and
I'm not sure.
Yeah, but because the effect of the sheared region, it extends easily to the wall. Okay.
Mm-hmm. But you can have dead zone with Newtonian fluid also.
Yes. You can have dead zones. It is mainly at the corners. So if I try a Newtonian fluid with I think a larger tank, yes, I might get dead zones here.
I think that with Newtonian fluid we can have a dead zone, but with Newtonian fluid we expect to have the same upward flow than the downward flow for the area, and so for the velocity. So I expect, but I'm not sure. So
in fact, for the sheared region, if I'm considering S1 for a Newtonian case, should it be of the order of the radius of the bubble? But it would depend on the radius of the bubble, because in this sheared region we have the bubble is pushing with it upward the flow.
Yes, okay.
You get that?
So I have some question about the simulation with open foam.
Yes.
When you use the B-viscous Herschler-Berkeley model,
yes,
do you implement your own model, or is it already available?
No, it's already pre-programmed. We only need to choose the rheological parameters and eta zero. So what we did is that we did a brief sensitivity analysis on eta zero to get the largest numerically acceptable value.
Okay.
Okay.
So I have a question about the elastic properties of the carbopole, because in this chapter of open foam, you present some experimental data about the elastic properties.
Yes.
But I think you don't use it in CFD simulation.
In fact, no. If you see that the numerical simulation part, it's mainly made of two things: building the model and validating it. It's not very well exploited, because exploiting all the capabilities of the numerical model will need a separate thesis. So it will need much more long time. And the numerical model, it's very interesting. So as I said in the further perspectives, that we can utilize it to find very different, like several local properties inside the fluid, but we didn't have all the time to do all of this.
Yes, but can you go back to your experimental results with the color lines for the velocity measurement?
Yes.
Because in these results,
wait, color line, which means this one.
yes, it's a very nice technique. Yes, it's very nice.
Yes.
It's a very nice technique. So just a technical question: how do you put the line initially?
It is so what I do is that I first on the top of the reactor I mark the middle, so the middle of this edge and the middle of this edge, just to make sure that it is in line with the injection pipe. Okay, then I place a track, which is an aluminum track. Okay, after that I devise something that I could move the track move an injection syringe along the injection track. I also tried an injection syringe with edge, so the edge have an angle, so in order not to inject directly downward and to create a very bad shape. So I want a straight line. Okay, so
Nice.
I can so it's something like that. I don't know. It's something like that. The injection syringe is something like that. I start next to the wall and I move the syringe along the track.
Okay, it's nice.
And this height is set as at HL/2.
Okay. Thank you. And I come back to my question about the elastic properties of the fluid,
Yes.
because here it seems that when the bubble rise in the liquid, after the bubbles, it seems that the fluid come back to the bottom of the tank, like in an elastic viscoelastic solids. So do you observe
Yes.
this kind of behavior experimentally?
In the numerical result, you mean?
No, experimentally, is there
Yes.
some
you mean some oscillations, like
oscillation in the
yes,
response?
Yes. In fact, in fact, when you have a high yield stress fluid, I tried once with putting some particles in the fluid at different locations, okay, and tracking these particles as each bubble passes. So I plotted the 3D trajectory of the particle, and you can see that during the passage of a single bubble, the particle will only move, but it's local, so it's not moving within the fluid. The fluid is only like compressing and decompressing by the passage of the bubble, so it makes a closed circle. And I had some results there, but I removed them for the time constraint. But I have some comparisons between a high inertia, low inertia, high yield stress, low yield stress.
Okay. So when you present the numerical results,
yes,
and you present the frequency and the bubble size for several gas flow rates.
Yes, so I think it's this one.
Yes. Yes. Do you try to check that the gas flow rate is equal to the frequency times the bubble volume? Because numerically you can check the accuracy by this way. Do you try to do this?
No, honestly, no, but I get your point. We can check it. But
it's to
yes,
have
we can
more
do it.
confidence in your results about the frequency,
Yeah.
for example, because it can be difficult to measure. I don't know, but
Yes, yes, but even because of sometimes you get the diffusivity between the two consecutive bubbles. But
yeah,
we
with
can, in fact,
volume of, and with the volume of fluid fraction, you can
yes, we can.
lose some gas, maybe, I don't know.
I can, I think, lose some gas. Yes, so there will be some error, of course, because the interface is not. So the model, in fact, it considers the refinement at the interface to try to capture as much as possible the interface of the bubble.
But I think it's a good way to check the balance of the gas by this way.
Yes, yes. I think we can try by sorting the alpha alpha is equal to 0 and alpha is equal to 1 and finding the
Okay.
volume of alpha is equal to 0. Could be done.
I have another technical question about the injection pipe.
Yeah.
Do you use a wall boundary condition in open form, or there is a pipe, or there is no pipe?
No, there is a pipe. There is a
There is a
pipe.
pipe.
So it is a wall.
We
It's
don't see
defined as
because we don't see the pipe in
okay. Yes, because I put a picture of the 3D model.
it's
But
okay. It's okay. There is a pipe.
yes, of course.
And just a last question about the last chapter. In all the work, you have a lot of data. You produce some correlation. I agree that these correlations are useful to summarize your data, but I don't agree that you use this correlation to extend the results to industrial scale.
Yes.
I think that the diameter of the bubbles are not will not follow the scale of the reactor, for example.
Yes.
So can you comment, please?
Yes. So I got your idea. The idea is that we are trying to extrapolate from results made on, for example, 10 liters reactor to something of 10 meter cube reactor, which is 1,000-fold larger. Of course, this is so we are asking something from the model that it cannot provide, but the idea, it was just put there as an example that okay, we can use these correlations. If not for an industrial reactor, we can use it for something like a pilot scale reactor, because we have an experimental scale, we can have a pilot scale, then we can have the industrial scale reactor. And I think, for example, Arcolia are working with something around the pilot scale with around 4 meter cube, 6 meter cube. So I think it is important to check the validity of these correlations as we increase in the scale. So because we cannot directly assume that the scale invariance is followed from 10 liters up to 200 meter cube, but it was just a demonstration of how we could use these results, for example, for designing at least the middle scale, the scale that is in between the industrial one and the experimental one.
Yes, but I'm not convinced by this comparison. I'm more convinced if you use open form, for example.
Yes. So open form will be the whole
take into account the scale up of the reactor with open form, but not with the correlation.
Yes.
So it's just a remark. I understand that it's necessary for the work, but okay.
Yes. So I tried also when applying the coloration is to choose a reactor in such a way that the Reynolds, the Oldroyd, and the yield parameter are still within the validity ranges of the correlations, just as a way to try to be more confident. Okay, that this will be similar, but it's not a tool to provide precise measurements. It is more or less an estimation, something like an order of magnitude or an estimation. But as you said, yes, the numerical model will solve this easily.
Oui. OK. Merci beaucoup pour les réponses et
Thank
les
you.
discussions et pour la très belle présentation orale qui était vraiment très intéressante pour se remettre les résultats en tête. Et voilà, donc j'ai terminé pour mon intervention.
Merci.
Merci beaucoup. Du coup, je donne la parole à Madame Audrey Sori, s'il vous plaît.
Merci, Monsieur le Président. Merci Ali pour cette belle présentation. Je ne vais pas redire ce qui a déjà été dit, mais c'était très agréable à suivre. J'en profite pour remercier vos directeurs de thèse de m'avoir invité pour participer à l'évaluation de ce travail. I switch in English. I understood
Yes,
that it was
exactly.
better for you. So congratulations, because it's huge work. And it's always interesting to see both parts of experimental works and then simulation about this process. Even if I agree with Arno Cox about the scale up of the process you proposed on the correlation parameters. You already had a lot of questions, and I will have only, I think, few questions, more general than specifics on the rheological study. First, one remark in your introduction, when you present the methanization process, there is no mention of literature at all. And I was quite surprised by that, because you explained the process in the first pages, and there is no paper associated with this.
Oh,
and I think there's a lot of paper in the literature that you can
yes,
mention.
yes.
And it was a bit surprising, but then you had a lot of literature mentioned, so no problem with that. You assumed that you carried your experiments at 20 degrees Celsius, and said that,
yes.
okay, you know that in the industrial process, the temperature is changing, but it's not a problem, as you said, something like that. I don't remember exactly, but you say that because you use a lot of different
Wide range.
fluids, I think.
Yes, a wide range of, yes, so we indirectly somewhat take that into account, because we used a wide range of yield stresses for the fluids. Okay.
Yeah, so you think that
in fact, so what happens is that as the temperature increase and the methanization process progresses, so in fact the large particle will tend to be smaller and smaller, and the temperature, when the temperature increases, you'll get a less viscous fluid, or a fluid with a lower yield stress. So in fact, in our case, because we don't have a jacketed reactor, we have a reactor with transparent walls, and we are working on a constant temperature. We considered a wide range of fluid yield stresses, a wide range of fluids with a low yield stress to somewhat simulate the liquid when you have a liquid with high temperature, for example, and the particle length is now smaller, and so it's probably something in the final stages of the methanization, and a high yield stress when it is in the initial phases of the methanization.
Okay, and what about the mass transfer? Because you said that there is no mention about mass transfer, but
in fact,
there is a reaction. Sorry, there are a lot of reactions in this reactor. And so what do you think about the impact of these reactions on the rheological behavior of the fluid?
Okay, so the mass transfer, in fact, I am the CH. It's a bit complicated. In fact, the thesis it's more concerned with the hydrodynamics. But if I want to think about it, we are trying to consume the substrate, so we are decreasing the total volume of the solid content to produce methane gas and some other properties. So the gas is released from the reactor. So the water content is decreased as a function of time, and also the particle size is decreased. So decreasing the water content will tend to make it more thicker thing. But also decreasing the particle size makes it less thick. So in fact, it's a balance between these two. The rheology of the am I in the right?
Okay, and do you think it's interesting to study it, or maybe it's too complex? For
In fact, if we need to study this, we should focus on one. Yes, to study this, in fact, we should. Okay, so now we are not going to take inertial effects and all this. So we need to put the hydrodynamics aside and study the rheology of the substrate as the reaction progresses. So I think it is sufficient to use a pilot reactor, which we are already producing methane. So the methanization is really happening, and try to measure the rheology of the substrate at different times as the reaction process. So I think we can do that using rheologie de grande dimension. So there's a way for measuring the rheology of the real substrate.
Okay, thank you.
Okay.
So I think I understood that you work with an industrial partner.
Yes.
So I didn't notice the. Yeah, I can check. Arcolia Energy. But I didn't understand if this study was for the design of the reactor, or was it already a reactor existing and it was for a better understanding, or for an optimization of this reactor?
No, the idea was that the reactor was already operational. It was placed, but some operation conditions, so some operating parameters. So, for example, how long, at what injection for it should we choose? How long should we inject? And these were not very understood, and even the flow inside the reactor was not very understood. So, in fact, we tried to use a setup, an experimental setup that is based on only one compartment of the reactor. So, in fact, the real reactor is large with multiple injection pipes. So we simulated one compartment, and we tried to see how does the fluid behave inside this compartment. So it was a way of gaining a first-hand knowledge on the hydrodynamics in the reactor that is already present. Okay, so they have a reactor, they build it, but the real optimal conditions for operation are not well defined. So it was a way of finding the trends and probably extrapolating the optimal conditions from this small scale reactor.
Okay, so it comes to my almost last question, is that you describe the perspectives of your work in a theoretical point of view. But what do you think about the perspectives of your study for the methanization process? That is the context of your thesis.
The idea is that, okay, the context of my thesis is based on the methanization, but the flow of non-Newtonian fluids, the paneumatic mixing of non-Newtonian fluids, it's present in methanization and water treatment in glass industry. So it's a wide range. So I tried to keep the perspective somewhat, because this type of injection, this type of mixing, okay, it's applied in methanization, but it also appears in several industries. So I don't want to be very specific on this one, although I included this industrial case that I included finally, which made all the problem. And this just to demonstrate that if we try to use it for a scale, this scale, we can use the correlations and SV. Okay, but because I didn't study the mass transfer of the methanization itself, I didn't study the reaction kinetics. So this is like another aspect of the total process. was focused with the hydrodynamics, the perspectives were in the field of hydrodynamics.
Yeah,
Okay.
of course, but I understand that. But what do you think? What your results can help? How your results can help to improve the process, or what would be the next step to go on?
The next step is to try to scale, to like simulate or do experiments in a scale in between my experimental scale and the industrial scale. So we can try, for example, in the pilot scale. So for example, in a reactor that's not 10 liters, but for example, 100 liters or 1 meter cube or something like that, of that order, and see how does these correlations change as we move from this scale to this scale to the industrial scale. In fact, we need to check for the scale invariance, that the scale invariance applies as we move up the scales. So if the scale invariance applies as we move up the scales, probably we can do some corrections, so some corrective factors for the exponents. We can finally be able to estimate the characteristics in the real reactor dynamics. So at this point, I am assuming scale invariant, but I'm not sure because I don't have the real experimental measurements in the reactor, in the industrial reactor. I have that in the experimental setup scale. So, and because the change from this scale to this scale is 1,000 folds, I think it will be interesting to have something in between. And I think Arcolia Energy worked in something in between. So whenever you try to study a process, you study at the small scale, something larger, something larger. You cannot directly move from 10 liters to 10,000 liters. It is.
Yeah, of course. So you are saying that your results are not directly usable for this process.
The idea is that they might be valid because, as I told you, the range of the Reynolds number, because we are treating the thing in a non-dimensional way, dimensionless numbers, and when we use dimensionless numbers, we are indirectly assuming scale invariant. So if for example I have real values for the industrial setup, I can either validate my verify my results or provide some corrective factors to the exponents. But I think the general trends, the effects of this and that, I think it works. Because the physics here should be the same as the physics here, but so you know it's
okay.
So if it's
yeah,
true,
I understand.
If it's true here, yes.
Okay, thank you. Last question. So finally, what do you think, mechanical or pneumatic mixing?
Oh, the $1 million question. I think, like in their case, so I was thinking, why do they use pneumatic mixing rather than mechanical? We can argue on the economics of the process, but it's not really straightforward for the economics. But I think because they have this thick fluid, whereas when you are trying to mix it mechanically, it requires a large torque on the motor first. Second, if the water content is low, it might create some gaps, and it will not really agitate the fluid. So the impeller will create some cavern around it inside the fluid, and it will not really agitate the fluid very well. I think this is why they tend to the pneumatic. So each one has an advantage and has its disadvantages. Another thing that they use pneumatic mixing is that I think it is a closed process. So they are injecting a part of the produced methane. So it's a closed loop. Even they use a single, for example, injection, a single reservoir for doing all of the injections. It can be easily automated. It is less prone to some, for example, to it needs less maintenance, so you don't have a moving part. In fact, you have a compressor, okay, and a reservoir, and the PLC that automates the injection each X minutes, for example, and you leave it like that. So it is it is easier to yes, something like that.
Okay, thank you.
Yes,
thank you for this. Yeah. Thank you for this interesting discussion. And, ok, je laisse la parole. Merci beaucoup.
Merci.
Merci à vous. Du coup, je reprends la parole, je la garde pour quelques minutes. D'abord pour remercier les gens qui vous ont accompagné tout au long de la démarche, hein, et qui sont présents ici avec moi, de m'avoir permis de participer et de présider ce jury. Alors, peut-être quelques commentaires généraux. Okay. D'abord sur la présentation orale, que j'ai trouvée effectivement très bien construite, très bien faite, parfaitement structurée, et qui, je l'ai dit au début, prenait en compte certaines remarques de vos rapporteurs. J'ai en particulier apprécié le fait que vous ayez resitué l'étude dans son contexte global de méthanisation. OK. Et j'ai également particulièrement apprécié le slide avec tous les nombres adimensionnels. OK. Et également, j'ai apprécié les vidéos et les illustrations graphiques que vous avez proposées complémentairement au manuscrit.
Okay.
C'est OK for you?
Yes, yes.
OK. Quelques commentaires pour le manuscrit. I was surprised, you know, because it was made as a series of scientific papers,
yes.
You know, and it's sometimes surprising. Not usual.
Yes, and there's another thing that the articles were not completed in the same chronological order that they appear in the manuscript. So this creates some confusion concerning the notations of the dimensionless number. That now you are talking R here is the bubble, and I tried to further correct that to homogenize everything, but this was the cause of that.
Okay, so as I'm not an expert, you know, in this field of research, I've got a lot of questions. We have no time for all these questions.
Okay.
Only one as an example.
Yes.
There are some dimensionless numbers I've ever seen before reading your manuscript. For example, aspect ratios for bubbles or for liquid.
Yes.
Are these usual dimensionless numbers?
No. The idea is that we are considering the dynamics, for example, for the bubble. So for the dynamics for the bubble are the velocity, the aspect ratio, the diameter. So we are trying to represent these characteristics in a non-dimensional way. So the aspect ratio by itself is a non-dimensional, so I can consider it as a non-dimensional number. Okay. So for example, for the frequency of the bubble, it is hertz. So I try to divide it by a characteristic frequency of the flow to get a non-dimensional frequency to be able to write it as a combination of non-dimensional numbers.
Following the questions by Professor Sorik, do you think that the combination between classical mechanical steering, okay, and the mixing by gas injection could be of interest from an industrial viewpoint?
The combination of the two?
Yes.
Well, I think if need be, in fact, we will need to check for the efficiency at each case. So in the first parts, when you have a very thick fluid with high solid content and this, we can use pneumatic mixing, for example. At this point, first there's a high quantity of the substrate, so there's too much food for the microorganisms, and it's not needed to have very high mixing at this stage. As the rheology decreases or reduces, we can put, for example, at the final stages, some mechanical mixing, because mechanical mixing it works well for Newtonian fluids, and so you will not need that large torque. But finally, whenever you are deciding any process, the final thing is that the economic cost of each one. So we need an economical study
Yes.
that compares the capex and the opex of each.
And at least, perhaps, a last question before leaving the floor to your
Yes.
supervisors. If you have to modify something on your experimental setup
Yes.
to intensify mixing of the liquid, for example, what would you put or change?
You mean that further develop my experimental setup to do liquid height? Liquid height, yes.
I think it's
not. In fact, I modified the setup. We started with working with only one size of the reactor, the smallest one. So then I had the largest one, the 61, and I tried to modify it to get a one in between. But I think it is more interesting to have like a column and check for the effect of the liquid height, because I think this will have an effect on the bubble dynamics themselves and on these. Yes.
Okay.
But if I want to treat the flow in a much to be much easier to study, I'll add a depth tube, because the absence of the depth tube caused too many problems, complications in the flow that made studying the flow very like unclassical at all.
En tout cas, je pense que vous avez fait un très bon travail. Il faut le dire en français. Very good job. Congratulations.
Okay. So,
la parole est à Monsieur Atou d'Arcolia Énergie. S'il vous plaît.
So,
merci, Monsieur le Président.
Can leave
Perhaps I will switch directly in English.
Yes.
Because I have no on the job which I've made, because we already had a lot of exchange during the thesis. So I will bring you more my feeling about your work. First, I would like to thank you for the work done during your thesis, Ali. Really, if I make some history of the process 8 years ago, due to the high viscosity of the used materials and the specificity of the gas injection, we built and developed the Arcometa process very empirically. At the beginning of the thesis, we had little knowledge, really little knowledge of the phenomenology of the flow inside the digester. And something which is important, and I will bring a precision of the process, the flow inside this digester, where the viscosity is very high, is a plug flow one. And compared to other devices which are used in methanization, the flow is a CSTR one, CSTR type.
Yes.
So, and this is very important because the plug flow of the materials is achieved by the gas injection, and that's why it's very fundamental for us to know the impact of the gas injection parameters on this flow. That's why the building of these dimensionless correlations is something very important. So if I resume what you have achieved during your thesis, Ali, you have estimated the cavity frequency, the cavity maximum diameter, the liquid viscosity, the ratio of the liquid mix by volume, and the circulation time. So
yes, and the bubble.
Really, really great job from my point of view. And I would like to underline the quality of the experimental work which have been done. And Ali, I greatly appreciated two things: the development of and the use of the colorimetric method on such materials. And it's not easy at the beginning. If you remember, it will not be easy to do things. And the second is your interest in showing how the developed correlations could be used on the industrial scale. And this is very important for an industrial like us. So numerical aspect for us is more complicated to implement, but with the numerical model you have developed, we have now an existing tool for designing reactors and setting optimal driving parameters of the digesters. It's a real opportunity and to go further on with these tools. Conclusion for your job, this work is very important for us because I think, and we started to do this, that it is directly applicable on an industrial scale. First, during your work, I think there is high quality experimental aspects, but also very advanced numerical simulations. For Arcolia, at the end of your thesis, we went from a very empirical approach to a computational approach of the process from an engineering point of view. And this is really important. And this is the objective at the beginning for us. So once more, thank you, Ali, for this great job.
It's my job. Thank you for your confidence.
Merci, Monsieur le Président, de m'avoir donné la parole et d'avoir pu donner mon sentiment sur ce travail.
Merci à vous pour ce retour dithyrambique.
Okay.
Il le mérite.
Qui prend la suite?
Ouais, je vais dire un mot très rapide, moi.
Cyril.
Donc, bravo Ali pour tout ton travail et notamment la partie numérique. C'est la seule partie où j'ai un petit peu contribué. Tu m'as étonné par ton autonomie vis-à-vis de tout ce que ça implique, le numérique. Donc, à la fois les aspects système, Linux, cluster,
Yes.
que ce soit le cluster du laboratoire ou au niveau régional, ou toute la partie liée à OpenFOAM et au post-processing. Très clairement, tu sors du lot par rapport à d'autres thésards pour ces aspects-là, cette autonomie et la facilité que tu as eu à prendre en main ces outils, parce que ce n'est pas facile. Et en plus, tu as eu des beaux résultats sur cette partie-là, donc j'espère qu'on pourra poursuivre par la suite avec Arcolia. On verra. Et donc pour tout ça, je te félicite. Et sinon, pour ta présentation, bon, c'est la 3e ou 4e fois que je la vois, donc je n'étais pas surpris, mais vraiment, tu as fait un super travail et tu as réussi à améliorer la présentation au fur et à mesure des répétitions. Et ça, c'est super, je pense, d'avoir pris en compte nos remarques. Et donc, bravo pour le travail. Merci. Et félicitations.
Merci.
Merci.
Bon, alors moi aussi, je vais le faire en français. Donc, je rebondis sur ce qu'a dit Cyril. Hein, donc, merci pour tout le travail que tu as effectué et la présentation qui, à l'image de ton travail, c'est-à-dire le transparent, très pédagogique et très clair. Et en plus, ça parlait un peu moins vite que pour les répétitions, mais c'est voilà. Donc, c'était vraiment très, très bien. Donc, moi, pour compléter sur les aspects numériques, parce que je félicite beaucoup, parce qu'au départ, ce n'était pas prévu. Hein. C'est parti d'une discussion en disant est-ce qu'on va essayer de faire des choses. Moi, j'avais fait les choses en 2D, ça marchait. Tu as pris les choses d'un vrai corps. En ayant su quand même ne pas dévier du plan initial, qui était quand même la partie expérimentale que tu as venue jusqu'au bout. Donc, avoir réussi quand même à gérer les deux sans te perdre finalement sur les deux aspects, ça, moi, je trouve que ce serait très bien. Effectivement, donc maintenant, tu nous donnes un outil qu'on a à exploiter, parce qu'effectivement, durant la thèse, on a plutôt validé l'outil par rapport à toutes les données expérimentales que tu avais. Et moi, je remercie beaucoup le jury d'avoir effectivement expertisé ce travail et d'avoir fait, on va dire, la soutenance dans des conditions assez habituelles, hein, à cause des conditions qu'on sait. Alors, je ne vais pas faire beaucoup de commentaires, mais c'est vrai qu'il y a beaucoup de questions qui sont revenues et qui, effectivement, sont pour moi fondamentales, hein, sur les aspects évolution des aspects révoluologiques, parce qu'il y a des aspects, je pense que derrière la question d'Hojeij, il y avait le couplage avec les réactions biochimiques et donc le process d'utilisation lui-même. Puis avec certaines questions, parce que les questions de M. Lee, les aspects tropiques, donc les effets d'histoire. Donc finalement, au fur et à mesure que le mélange se fait, surtout avec le vrai produit industriel, où il y a une phase solide et une phase interstitielle, comment finalement la ségrégation peut amener à des évolutions rhéologiques à prendre en compte. Et c'est vrai que l'outil numérique ici, il est peut-être un outil, alors pas le seul, mais qui permet peut-être de regarder ces aspects-là plus facilement pour la partie expérimentale. Donc toujours aussi, à travers cet outil, je pense des perspectives. Donc je vais m'arrêter là parce que je pense qu'il y a beaucoup de choses qui ont été dites et je te félicite encore. Ça a été 3 ans et quelques très agréable pour travailler. On a bien pris en main le sujet et c'est vraiment bien. C'est bon.
Merci.
Merci.
Voilà, donc bon, je peux dire un mot également. Donc bon, Ali, bravo pour tout le travail que tu as effectué. On se connaît depuis déjà 4 ans, parce que je te connaissais déjà en tant qu'étudiant du master FME, là, dont je suis responsable, et puis ensuite tu as enchaîné sur le stage de master qui a permis de bien poser les choses, parce qu'il y avait un pilote qui existait déjà au laboratoire, sur lequel avait travaillé déjà 2 stages de master et puis un autre stagiaire, mais bon, c'était un peu compliqué, on n'y arrivait pas vraiment, et puis quand il est arrivé, on a posé bien les choses. Il a su faire évoluer le dispositif, l'améliorer, l'instrumenter, passer d'un système qui était à pression imposée à un système qui est à débit imposé maintenant, et ça a permis de bien aider. Et tout ça, il l'a fait avec à chaque fois beaucoup d'autonomie, comme ça a été souligné par Cyril sur l'aspect numérique. Je veux insister sur le fait que sur l'aspect expérimental, c'est exactement pareil. Ali, on lui dit, tiens, il y a ça qu'il faut regarder, et puis on revient une semaine après, bah, c'est fait, il a éventuellement acheté la vanne qu'il faut, il propose des améliorations, et puis il ne se contente pas de les proposer, il les met en œuvre, quoi. Donc, typiquement, les méthodes de la colorimétrie qui ont été évoquées, bah, voilà, on n'a pas eu à lui dire, tiens, on pourrait faire comme ci, on pourrait faire comme ça. C'est lui-même de son plein gré qui, tiens, je vais faire ça, et puis ça marche. Donc là-dessus, je voudrais vraiment te féliciter pour ce très grand degré d'autonomie, puis ton ingéniosité. Également dans le traitement des données, parce qu'il y a eu beaucoup de résultats. Il y a beaucoup de vidéos, il y a eu du traitement du suivi de particules qui a été fait, et là-dessus, ben, tout seul, tu as su aller chercher les outils numériques disponibles sur Internet ou autres pour les mettre en œuvre et puis sortir des données quantitatives qui ont permis de produire au final donc 3 publications et puis une qui est encore dans les cartons. Donc voilà, très grosse quantité de travail. Là, il y a un certain nombre de résultats qui sont présentés, valorisés. Donc il n'en a pas parlé parce qu'il est un peu modeste, mais à côté de ça, il y a aussi tout un tas de choses qui ont été faites. En particulier, on avait également regardé les suspensions, on avait du suivi de particules. Donc tout ça, c'est énormément de temps qui a été consacré pour mieux comprendre ces écoulements. Donc voilà, pour tout ça, je te félicite. Je voulais également mentionner rapidement au passage qu'il y a eu quand même la phase du confinement qui a été un peu déstabilisante pour chacun d'entre nous. Et bien Ali, là, finalement, bon, ça a été un peu difficile comme chacun d'entre nous, mais rapidement, en fait, il a su mettre cette période à profit et puis voilà, on était un peu coincé côté expérimental, c'était pas possible de venir au labo, ben, on est parti sur le numérique et puis ça a donné les résultats que vous avez pu voir aujourd'hui. Donc voilà, il a toujours fait preuve d'enthousiasme et de motivation pour ce sujet. Donc voilà, maintenant, bah, écoute, une étape de franchie. Je te souhaite une bonne continuation dans ta carrière et puis encore bravo.
Merci.
Donc voilà, je vais m'arrêter là.
Eh bien, merci.
Okay.
Merci.
So,
Du coup, on va délibérer. On va vous demander de quitter la salle, si vous voulez bien.
Ok.
Et puis, on va revenir au regard de la qualité de vos travaux, d'accord, aussi bien dans leur dimension expérimentale que numérique. au regard de la présentation que vous nous avez fait aujourd'hui de très grande qualité, l'ensemble des membres officiels de ce jury vous décerne le grade de docteur de la communauté Université Grenoble-Alpes, donc dans la spécialité mécanique des fluides énergétiques procédés. Et en leur nom, je me permets de vous adresser oralement nos félicitations pour l'ensemble du travail que vous avez réalisé. Donc bravo à vous.
So I just want to thank the jury for their time, for their agreement to evaluate my work, for their insightful comments. Big thanks to my supervisors, Monsieur Laurent Jessic and Philippe Sachet. I am honored to complete the PhD under your supervision. And I consider myself very lucky because you were always there unconditionally, even sometimes when I was a little bit not the perfect student, but your guidance. Also for Cyril, thank you for your help, especially in the numerical case and in the preparation of the science. And I want to thank my friends who attended and now are preparing the post. Those who could attend and those who could not attend. And finally, I want to thank France because it allowed me to really pursue and fulfill my dream of doing a PhD. So thank you all. I'm really honored. Thank you.
Bravo.
Eh bien, merci à tous pour votre participation active. Je ne sais pas comment ça se termine cette histoire à distance. En termes de convivialité, je vous accorde que c'est assez limité. Du coup, en tant que président, je vous remercie en tout cas pour votre participation active. Je remercie les rapporteurs en particulier pour le travail d'expertise sur le manuscrit. Et puis, il me reste à vous souhaiter à toutes et à tous une bonne fin de journée. Et puis, restez en forme. Voilà.